Welcome back to Mechanics and Control of Robotic Manipulator. Last few classes we have seen kinematics and dynamics. So this particular class we are going a little ahead where we are going to touch upon the control. For doing the control we should actually have some principle called the trajectory planning, or you call trajectory generation. So why the trajectory is coming and what is the difference between trajectory and path and how we can generate the trajectory, these all we would be covering in today's lecture and a few other lectures upcoming. Okay, so in that sense what we are trying to cover here basically why we need trajectory generation and what is trajectory generation, and we would be seeing one trajectory generation principle called cubic polynomial function. So these are the things which we are bounded to cover in this particular lecture. So let us actually move little ahead. So what is trajectory? So trajectory is nothing but a path with a function of time. For example, now I say that, so this is what you call time versus x. So I am saying that this is actually like having this. So now this is actually like time history. Okay. So this is going to give a trajectory, but right now I say that this is actually like not time dependent. I said some parameter called s. So this is actually like vary 0 to 1, and I am actually like writing the same thing as x. So now this is actually like not dependent on time. So in that sense what it is called actually like a kind of path. But why this is required? Because the robot controller actually like need to follow certain things, right? So for example, now I am saying that the manipulator is supposed to grab this particular point from this point. So it need to actually like come and do this. So for coming this, you need to actually like identify some kind of predefined path, or you call trajectory. So why this is required? Because sometime there would be obstacles, so it need to go, or probably in order to make the energy optimal or time optimal, so you need to have some predefined manner of, you can say, following one point to another point. So this is what the prerequisite. And when you talk about controller, so you have all the time actually like some desired and you have actual. So you are actually trying to compare and trying to maintain the q actual become q desired. So this can be actually like just a constant. For example, you take a air conditioner, you keep 20, 22, 24 or 16. So these are actually like set, right? So then the air conditioner is supposed to follow this in a, you can say, piecewise manner. Whereas you assume that you are actually like taking a probably a milling machine, or you are actually like trying to draw a diagram. So then you have to actually like follow certain manner, right? So then this is actually like each and every time would be actually like defined. So these all we are trying to see. So that's point we are actually like bringing it here. So now we are talking about the motion. So the motion is actually like what we bother. We bother about actually like the position and its derivative, which is actually like velocity. So these two things are very important. Even if you are going for a dynamic level, even the desired acceleration also important. So then you can see like, so acceleration is the third part which we are bringing in. So in that sense we are actually like trying to see these all. So for that we are actually like going to specify the robot position as a function of time. That is what we are going to call as a trajectory. Okay, so now you can actually like understand the trajectory can be given one way of definition. It is nothing but specification of a robot position as a function of time. That is what we are calling trajectory. So then we need to actually like differentiate what is path and trajectory. So for that we are actually like taking the trajectory means, so we take a q is the, you call the position. So the q of t is actually like given where it is starting from 0. It need not to be 0 all the time. So I said the starting point is t0 and it is actually like ending as tf. So where I define this q as actually like t, so the t vary from t0 to tf. So this is what we call trajectory. So in the sense is it time dependent, in the sense you can see it's a function of time. Now this tf and t0 I actually like converted into 0 and 1, and this I actually like call q of s. So where there is only, you call subset of s, that s actually like vary, you can say 0 to 1. So if I make this, you see that the time dependency is gone and you no need to actually like bother, even it can be easily scaled up to any given time range. So this is what we call actually like path. It is need not to be function of time. So that is what we are calling like path. We can actually like rewritten as another set of function, the q of s, where s actually like belongs to, or you can say s is vary 0 to 1. So how we convert the t0 we equal to 0 and the tf, or you can say tf minus t0, so that we are actually like equating to 1. So now this is what we call time scaling. So most of the cases we do the time scaling. So because the path easily we can generate with respect to 0 comma 1, or the s is varying 0 to 1, that way we can generate, and we can actually like scale up whatever way you want. For example, now my end effector supposed to move in 10 degrees per second as the, you can say, speed. So then I can see what would be the time required. I want to actually like increase the speed of that system, then I can actually like change the time step, like that I can make it. So that is what the whole idea. Here we are insisting the, you can say, robot position as a function of time. That is what we are focusing as a trajectory here. Okay. So in that sense, so either you call q of t or q of s, that should be at least twice differentiable, in the sense the acceleration is definite. In the sense, so acceleration is actually like what you call finite value, or it is function of time, it would be there. So in that sense, your actuator will start in a proper way. So that is what we are actually like putting it. So in that sense, we are actually trying to see a little more in detail. So what that means, so we are again bringing back the different definition. So you should actually like should be familiar. So the trajectory is nothing but time history of position, velocity and acceleration of the end effector, or sometime it would be actuated joint. It depends on what space you are actually like working on. So for example, you are working on a configuration space, then the, you can say, time history of you can say actuated joints, in the sense joint position, joint velocity and joint acceleration we write in time history. That is what you call trajectory. Or you are actually like bothering about the operational space, where the end effector point, you can say the position, velocity and acceleration need to be generated, then that is actually like end effector trajectory. So that is what we are seeing it. So in that sense, what would be the main concern? So I said it's supposed to be twice differentiable, but what if you are thinking about in terms of real time implementation? So one is ease, so it's supposed to be ease of generating, and it should have a flexibility. So that is one important point we need to think about further. So when you generate any trajectory, the trajectory should be very smooth. So in such a way that the robot manipulator or even robotic system, that should actually like take away from the jerk. So for example, now you take a car and you start and you actually like release the clutch arbitrarily. So what happened? There would be a small jerk, right? So however, if the experienced driver, you can see that there would not be any, you call jerk you can experience when the car is starting, right? When start moving. So that is what you call the smooth trajectory. So in the sense, your trajectory should be smooth, so that you can avoid the jerky motion. Invariantly it will actually like reduce the cost of, you can say, overall system, and long life of the actuator will come. Okay. So that is what the whole idea. So further in terms of actually like real time, you can say computational point of view, so it should be efficient. So the representation of the algorithm or the trajectory planner should be efficient, and as well as it should be actually like fast enough. In the sense, the processing time for computing should be actually like good. So that is what we said, ease of generation in real time, so that you can easily implement it any point of time. That is what the whole idea. So just to take that, so what would be the easiest one? So I have x of t, so that is actually like varying x naught to xf. I am just saying. So this is corresponding to t0 and this is corresponding to tf. So what would be the easiest one? So we will say that what is xf minus x0. Okay. So this is actually like tf minus t0. So this I call as a slope, in the sense linear interpolation. So then I will actually like take it as a function of time. So this would be x naught plus this is what x of t. So now in that case, what it is giving? It is giving a linear interpolation. But this linear interpolation is giving what? So it is actually giving a constant velocity generation. If you think about constant velocity, what would be the acceleration? So it would be infinite in both acceleration and deceleration at initial, and at the end also infinite deceleration and acceleration, right? In the sense, so your acceleration at initial and end point should be infinite, which is not possible. You don't have a smooth curve. So for that only we are actually trying to see. So whatever I have written in actually like analytically, so that we can see in symbolic or you can say graphical manner. So this is what I said, the initial point, and this is the final point of x of t, and this is their duration which I want to actually like see. So what is the one of the easiest one? I connect as a straight line, which is actually like really a better one. But what happened, the velocity would be a constant. When I actually like draw time versus I start t0 to tf, so the velocity would be constant, right? So if the velocity is constant, what would be the acceleration? So the acceleration would be, so infinite acceleration and deceleration. So similarly here it would be, so that is actually like a little concern for us, okay? So this is actually like velocity and acceleration. So in order to avoid that, what people are actually like thinking about, this is what the linear interpolation. So in order to actually like get this, so the t naught we always assume 0. So but if it is t naught is there, then you have to actually like substitute that. So not simple t. So I'll just rewrite this equation. So this is actually like minus t naught, okay? So that you can actually like get it clear. So now in that case, so what we are actually like writing, this is linear interpolation, this is not smooth, it is actually like a jerky motion. So in order to avoid what one can see, so there are actually like several possible, you can see these 2 points can be connected like this, okay? So like this, and there are several possibility to reach from this. So we are trying to see what would be the efficient. So this is actually like first order. The second order is possible, which is what you call the quadratic equation, but quadratic equation would be having, so the number of, you can say, equation and number of unknowns are actually like not properly matching. So we'll go with you can say cubic polynomial, where the cubic polynomial, the equation I can write, so a naught plus a1 t plus a2 t squared plus a3 t cube, where t naught I assume as 0, so which is I call this. So in the sense, what you can see, there are 4 unknowns. So these 4 unknowns, what I can do, x of 0, x dot of 0 I can equate, and similarly x you can say x dot of tf and x of tf I can actually like substitute. You can see, so 4 boundary condition and 4 unknowns I can get it. So that is what we are trying to see. So in that sense, the cubic polynomial which I have shown, it is very smooth, so which is actually like very close to what you call the straight line, but it is actually like very smooth. It is actually like going to give at least twice differentiable, in the sense the acceleration would be finite, okay? So that is what we are trying to see here. So in the sense, what one can see, this is what the equation which we generated. So in that sense, you can actually like see, so these 4 unknowns we can actually like calculate by bringing the you can say 4 conditions. So I call this is x naught, and this is xf, and this is x dot of naught, and this is tf. Okay, so then xtf is called xf. So in the sense of 4 unknowns, and we can actually like get, you can say 4 equation, and then we can solve. So that is what we are trying to write it here. You can see further you differentiate, so what will come? So further if you differentiate, so it would be actually like further if you differentiate, so the equation x of t is actually like, so a naught plus a1 t plus, I am just assuming that t naught is 0, okay? This is explicit assumption here, otherwise I have to write t minus of t naught. So in order to avoid that, I am writing, so what would be x dot of t? That would be a1 plus 2a2 t plus 3a3 t squared. What is the x double dot? So that would be, so 2a2 plus, you can say 3a3 t, right? So this will be, sorry, this is 6. So this will be coming, but you need actually like only 4 equations. So we will actually like take this and this, and we can actually like substitute and you can do it. So now for solving this there are several ways. So one of the easiest way what we can do it, we can rewrite this in a state space form. So what we can do, so we can write the unknowns, so a1, a0, a1, a2, a3 are, I can write it one side, and the other side actually like x0, x dot of naught, and xf dot I can write. And you can see the first equation, it is 1 0 0 0, the second equation 0 1 0 0, and the third equation 1, then you can see tf minus t naught and tf minus t naught squared, and the third one is tf minus t naught cube, and the third one 0 1 and 2, so tf minus t naught, and this is 3 tf minus t naught square, right. So now this is actually like linearly independent you call rows containing. So in the sense this I call A, so the determinant of A is actually like non-zero, okay. So in that sense what one can see, so if I take inverse of this and multiply with this, so that will give A0, A1, A2, A3. So that is what we are actually like doing it. So you can see I take this A inverse, so this A inverse I multiply with this and I can do. For making a simplification, I assume T naught is 0 and initial velocity and final velocity are 0. So in that sense what happened, x dot of 0 and x dot of f both are 0. So which gives the A naught, A1, A2, A3 in a simplified manner, okay. So the same way you can actually like even you put it non-zero value, but T naught we can make it always 0 because we can actually like bring it T naught at the end wherever it is required. So in that sense you can actually like assume x dot of 0 and x dot of f are exist. So then the A0, A1, A2, A3 are obtainable in this way. So now you know all the coefficients. Once you know the boundary condition, then what you can do, you can actually like generate the trajectory. So that is what we have done in the here. So this is what you call x of t as a cubic polynomial. So now this equation actually like arrived. So now we will actually like go back individual component. So in the sense how the velocity, how the acceleration will come, because the position profile we have seen. So now I assume that it is scaled down to 1, okay. So in that sense t0 I assume 0 and tf. So this is the duration, and the s displacement, or you can say x of t as the, you can say displacement as 1. So then you can see the profile, it is smooth. So now if you rewrite this into a velocity form, you differentiate, you can see the velocity would be maximum at the middle of the duration. So that value would be equivalent to 3 into 2 tf, and even you bring the non-zero initial condition, all those things will come, theta f minus theta 0 would be added, okay. So now the same way you go to acceleration, you will feel a little strange because the acceleration will start from non-zero value, okay, and similarly end with non-zero value. So now we assume that this is actually like 1. So based on that you can actually like see that the acceleration is actually like non-zero at initial phase and non-zero at the final, and 0 acceleration at middle point. So here actually like you can see the middle point, it is actually like this curve is actually like making another parabolic. So it is actually like positive parabolic and this is negative parabolic kind of thing, it is generated. So now this is actually like proper what you call cubic polynomial. This is giving a smooth profile and it is actually like you can say twice differentiable. In that sense this is one of the easiest way to apply. So most of the industrial manipulator used cubic polynomial, that's why we straight away started talking about this. But the problem here is we don't have any control over the initial and final acceleration. So if you want to do that, so we need to go little you can say improvised algorithm that we will see in the next lecture. But now we will actually like go further. The cubic trajectory can come with via point. For example, I said that, so this is theta 0 or x 0 whatever. So I said this is actually like supposed to reach here theta f, but I given a via point as theta v, okay. So then how I can actually like do, so even the cubic trajectory can be generated in two mode. One is this what you call via point velocity also specified, then that would give actually like you can say 8 equations and 8 unknowns, and you can actually like solve it, and that would give slightly a trickier way that we will be seeing in the next slide. But the other one is actually like the velocity of the you call the via point is not specified, then we can see that the velocity is what generated from here, that we can continue as that is the velocity, in the sense the initial acceleration and velocity of the second segment would be the final acceleration and velocity of the first segment. That way we can equate, so that would give further add on that make life simple. Okay, so that is what we are trying to see. So in that sense you can see in the case 1 there may be a discontinuity because you are specifying the what you call the via point velocity, that make the joint acceleration is actually like jerky. So in the sense, so it end here and another one end somewhere like this. So this is the first segment and this is the second segment may come like this, we can see that. So this is actually like going to give a discontinuity which is not encourageable. So in the sense this point is discontinuous happening. Okay, so whereas the second one, the final velocity and final acceleration of the via point would be equal to the initial velocity and acceleration of the second segment. So in the sense we can actually like use this way. So in that sense it is actually like give the smooth transition, and as well as the acceleration would be for example this way. So it comes like this, it goes. Okay, there would not be any discontinuous happen. We can see that how it actually like happening it, right? So in that sense we take the via point segment. So you can see like we take first one with the velocity specified. So then you can see like this is actually like solved as a independent cubic polynomial, then this is actually like solved another independent cubic polynomial, and you can actually like use it. So in the sense, so you have first set of equations, so T0 to TV. Okay, the second segment is actually like TV to so TF. So that way we will make it. So in the sense x of you can say t would be contained actually like x of 1 for actually like the first duration, so T0 to TV, and x of you can say 2, that would be so TV to TF. Okay, so like that we can actually like use it. So in that sense you have actually like via point velocity. So in the sense I said that x1 of T0 is actually like x of 0, and x1 dot of T0 is so x dot of 0. Okay, so x1 of TV is xv. Okay, so in this case it is actually like I will write it consistent. Okay, so I'll just use the consistent in the sense I'll write so theta, so I'll write it this again. So theta you can say T0 is actually like theta 0, and theta dot T0 is actually like theta dot 0, and theta of TV is theta v. Okay, so theta of TV is defined like this. Okay, so second segment is actually like so you have 6 variables. So second segment is actually like TF, which is you call theta f, and so these all 6 variables would be given, but based on this how many equations you can generate. So you can actually like take this is the first segment, so then you can actually like make it, so then the second segment can actually like do it. So in that sense you will get 8 unknowns and 8 equations, you can solve it. So the profile will come like this. So based on that velocity you can see, as I already said, there is theta dot v exists. So you can see like it is first curve is smooth where maximum at the middle. Okay, so where you can actually like see, and after that what happened, the trajectory is actually like second segment where it is start from non-zero via point velocity and end with the theta f, it is actually like going again. So here itself you can see that there is non-smooth transition. So that is what we can actually like see it from here. You can see this is the first segment acceleration and there is a discontinuity happened at this point. Okay, so this is the second segment acceleration and this is the first segment acceleration. So there is a discontinuity happened here. So in order to avoid this, what we can actually like do it, So we can assume that you can say the final velocity of this segment and final acceleration of this via point would be equal to the second segment initial velocity and initial acceleration. So in that sense, you would be using even the you can say acceleration equation and one another you can say constraint. So then what happened, you would be getting again you can say 6 valid equation, and you can add these 2 additional constraint. So then it would give 8 equations and 8 unknowns, and then you can solve it. So I will show you in the simulation how these variables and all generated. So now based on this, you can see the velocity is actually like smooth enough, okay, and you can see even the acceleration is actually like, so no discontinuity is happening. So this is what we call actually like a cubic polynomial with via point. So we'll see how the cubic polynomial used in real time. So real time we usually uses in a nested. So before going to the nested, we can see one another constraint. So where a2 and a3, if you recall the variables, so it comes actually like a tf squared in the you call denominator. Similarly, t3 tf cube are in the denominator, which makes, so when tf is actually like very large, what happens, this becomes actually like infinity, in the sense this a2 and a3 approximately to 0, which we need to avoid. So for that, what we used to do, so we will actually like take one of the variable, new variable called u, okay. So in order to avoid this tends to 0, so then what we are actually like trying to take, we are trying to take x as t by tu, and in that case what happened, this is actually like a path. So now you got it why we have used so q of s. So now in that way, so it is 0 to 1, so in the time no need to actually like worry. So now simply you scaled up to tf. So now you want t, then that is u into tf, right? So that way you can actually like multiply. So based on that, what happened, so your equation would be very simple. So we write that x of u in the coefficient of b0, b1, b2, b3. The coefficients you can see like there is no divisions, right? So in that sense, it is actually like very simple, and even this we can rewrite as a nested form. So I am writing b0, okay, so plus u, you can actually like see that b1 plus so b to u, then I can actually like write plus that way. So like that I can write as a nested form. So you can see this nested form is actually like one of the easiest one. So in this nested form, what you can see, so first one addition, then multiplication, then addition, another multiplication, okay. So here one multiplication, so first you multiply this, the first operator, then second, then third, the fourth and fifth and sixth. So in the sense, what you can see, 3 multiplications plus 3 additions only coming, so which is easy to derive the equations in real time. The computational point of view, it is very easy. So that's why we are using this nested. Even this nested is making even you can say very simple, because the you call the velocity and acceleration also like contain only 3 additional multiplication and you can say additions only. So in that case, we can easily solve this all. So if that is what we actually like bound, so then what you can actually like see that this can be easily implemented. So now you have actually like seen so how the cubic trajectory has come, but I already said the cubic trajectory is actually like not having any control over initial and final acceleration, so that we can think about some kind of higher order you can say polynomials or some other polynomial. That is what we are going to focus in the next lecture. So once that is done, then we will bring back to the manipulator and see how to generate the trajectory in joint space, or you call task space. So with that, I am ending this short lecture. See you then. Thank you. Bye.